Today we're gonna study self-induction and RL circuit. Okay, so for self-induction, let's see if you have like some power supply. Here is a power supply. Okay, and then you have some coil or an inductor. This is a coil. Let's make it a power supply. Let's make it variable, like the current is an AC current. So the power supply changes like sinusoidal. It goes up and down. So this is E. So we have some current that's changing, that's coming in to this inductor. This is the inductor L. Now, I told you last time in the previous video that the inductance L is equal to the number of coils times the flux. This is the magnetic flux over the current. So we can take this N, the number of loops, like here we have 3, number of loops, times the flux, the magnetic flux, is equal to L times I. Now, from Faraday's law, we know that E, this is the electromotive force, is equal to minus d phi. We can put N if we want to. We can put the number of coils here, N d phi over dt. And this N here is the number of coil. So you can see here, we can change this equation to this, minus the number of loops times d phi, this is the magnetic flux, over dt. This is Faraday's law here. Now, we have the flux here and we have it here. So what we can do, we can take this flux, we can say the flux FB, phi B, is equal to Li over N. We take this flux and we put it here. So we get minus N d dt. And then I put this flux, Li over N. Now L is the inductance, is constant, it should come out. This N here is the number of loops, cancel N. So we have E is equal to minus, this N cancels. dL, I put here L, I put I, and here dt. Like I said before, this L is fixed. So I put minus L di over dt. So a change in current induced or created a voltage in this coil or this inductor. So a change in current created a voltage in the inductor. Okay, so that's why it's called self-inductance. The solenoid itself, or you can say solenoid or you can say inductor. The solenoid itself created its own voltage due to the changing of the current. Now, what we do, we're going to study the RL circuit. This is resistance and this is inductance. RL circuit. Okay. Now for the RL circuit, I have to be careful here with the presentation because we have some calculations to do. So I need to draw some RL circuit. So here is again the power supply. Here is the resistor. Here is the inductor. So this is an RL circuit. Okay, this is R and that's L. Okay, now this voltage here is gonna actually distribute itself. Some of it will go across the resistance and some of it is gonna go across the inductance. So we can apply Kirchhoff rule. So we have one loop here. We apply Kirchhoff rule. So here is the loop. Okay. And then we start with E. This is E. Minus the voltage across R. The voltage across R is Ri. We have a current here, I. It's coming down. And then minus the voltage across L. But the voltage across L is this one. Okay? Now what we did, what we're going to do, we're going to just look at the magnitude. This voltage here get distributed. Minus that voltage equal to 0. So we just use magnitude. Minus Ri minus L di over dt is equal to 0. Remember, we have a minus sign here for E already. But what I'm doing, I'm using the magnitude. So I have some voltage here. I took it as magnitude, voltage, magnitude. And then the sum of them is equal to this voltage that I started with. Okay? So now I can change the equation a little bit. I can put here L di over dt plus Ri minus E is equal to 0. Let's divide by L. So this will give me di over dt I plus R over L I minus E over L is equal to 0. Now you can see this is a differential equation. We have the variable, we have the derivative, this is the function, that's this derivative in some equation. Now what we do, we can change this differential equation. We can write here di over dt. Let me go up a little bit. di over dt plus, I factor out this R over L. So I put here R over L as a factor. And then I put here I minus E over L. And then I multiply here by L over R. And this is equal to 0. I just factored out this R over L from here and from there. Look at L. L cancels. So this will give me di over dt plus R over L, open bracket, I minus E over R is equal to 0. I changed the differential equation. I made it simple. I made it homogeneous. I'll show you why. You see here, I can change these variables. I can make this I prime. This current here, change it to a different current called I prime. Now remember, this E over R is constant because this is, we can take the voltage to be fixed, like some fixed voltage coming into the inductor, okay? And this R here is also fixed. So when I take the derivative, follow me carefully here, please. When I take the derivative of I prime, and since I prime is equal to I minus E over R, it's like I'm taking the derivative of I because this is constant. So the derivative of I prime with respect to time is equal to the derivative of I with respect to time because this is fixed. Let me show you. If I do di prime over dt is equal to d over dt of I minus E over R. Remember, this is constant, so I get di over dt. Now, let's, instead of putting di over dt, I'm going to put di prime over dt. So I put here di prime over dt. See, I have di over dt, but I'm putting di prime over dt plus R over L I prime. Remember, this is I prime is equal to 0. Now look at this differential equation. It's homogeneous. It's simple. It's easy to solve. We just separate the variables. So I put here di prime over dt is equal to minus R over L times I prime. Okay, so this will give me di prime over I prime is equal to minus R over L dt. Now, I use an integral. I'm looking for I, but for me to find I have to find I prime. And then after I find I prime, I make it equal to I minus E over R and find I. So on the left side, I get logarithm of I prime. On the right side, I get minus R over L times T plus some constant C, constant of integration. Okay? So I'm looking for I prime. So I have to introduce the exponential because the exponential of the logarithm of I prime is just I prime. So I put here exponential of this will give me I prime is equal to exponential of minus RT plus C together. But what is this? This is e to the power C, e to the minus R over L times T. This e to the power C is just constant because what is e? E is just 2.7. It's just a number, and to the power some constant is going to be constant. So I can just put here I prime is equal to some constant k, e minus R over L T. Let me bring the paper up. Okay. Now we found I prime. I prime is k e to minus R over LT. Now this I prime, remember, over here, I prime is equal to E minus E over R. So I put here, I'm using this equation. I minus E over R is equal to K E minus R over L times T. This is the inductance resistance. Now, this K is a constant. In mathematics, it's just constant. But in physics, it has a meaning. What is it? We need to know what this K is. If you think about it, this K is actually a current. Okay? Look at here the equation. This is current. This is Ohm's law. V over R is a current. So there's got to be some current. So what we do, we need to find this K. So we do at time t equal to 0. At time t equal to 0. What's happened? We have to go back to our RL circuits. So I go back here. At time t equal to 0. The current is about to leave, so it didn't get there yet. So at time t equal to 0, the current is 0. So I put here, I go back here. At time t is equal to 0, the current is 0. So I put 0 minus E over R is equal to K. E, time t equal to 0, I put 0 because time is 0. But E to 0 is 1. So this K is equal to minus E over R. We found K. You see, remember Ohm's law, so this K is current. So we take this K, which is here, and plug it here. So we take this, then we plug it there. So now, I go back to this equation. I is equal to minus I minus E over R is equal to K, which is minus E over R, times E to minus R over L times T. Now we need to fix the equation. So what do we do? I put here I is equal to E over R factor. I take this one here, 1 minus E minus R over L times T. So here is the current. We found the behavior of the current in the inductor. This is the behavior of the current in the inductor. Now, let's study this equation, see if it makes sense. At time t equal to 0, we put 0 here. E to 0 is just 1. 1 minus 1 is 0. So at time t equal to 0, the current is just 0 because we have 1 minus 1 is 0 times that is 0. Makes sense. At time t equal to 0, the current didn't come out. It's about to come out of the bearing. So we don't have a current. Now, at time goes to infinity, when t goes to infinity, if t goes to infinity, this E minus R over L times t will go to 0. This will go to 0. If t goes to infinity, this will go to 0. Makes sense because e to minus infinity is 1 over e to infinity, and e to infinity is u number, it's infinite, so this will go to 0. Now, at time when t goes to infinity, I put here t goes to infinity or large, the current is just E over R. Now what's so interesting? When you allow more time, that inductor, it's like doesn't exist, it's like a wire. So look, we have when t goes to infinity, when t is large, we just have Ohm's law. So the circuit, we put here E, and we have resistor R, inductor L. So when t is very large, the circuit becomes just this. E, we have a resistor and no inductor, just a wire. So when t is large, if you allow more time, the inductor doesn't react anymore. It becomes like a wire. So you don't have change in flux. So you don't have that voltage across the inductor because it acts like a wire. So the potential here will be the same as the potential there. So you have difference of potential is just 0. So it's like a wire. So the current just be passing by. Okay. Now we can plot this behavior of the current. Let's plot it. So here I put the current I. Here I put the time t. And then I go to the equation. At time t equal to 0, this is 1, 1 minus 1. So I start here. This is 0. At time t equal to 0, I don't have any current, so I start here. Now, when time goes to infinity, it becomes 0, and the current will just become E over R. So here I have E over R there. So this E over R will act like an asymptote. It's going to act like an asymptote. It's blocking the curve from passing through. So the current will increase, keep increasing, and then it's going to be blocked by this asymptote. So you have a limitation on the current. And what is that limitation? Is I E over R. It cannot get bigger. So the current will increase to a certain amount and then it stay like that. It doesn't go down. For it to go down, you have to shut off that battery, turn it off, so it won't give the electromotive force to the circuit. So this, one thing I forgot to mention, you see here this equation? They write it differently in books. They write something like this. They put I is equal to E over R. They put here 1 minus E minus T, and they put here tau, this Greek letter tau. This tau here is equal to L over R. And this tau here is a time constant. I put here time constant. It's like what we did with capacitors. With capacitors, we found that tau for capacitors is equal to RC. But for inductor, tau is equal to L over R. Okay?